Assalamu alaikum. Is everybody there? And can you see this slide number 9?
Yes, sir.
All right. So yesterday you have come across two different types of the electrophilic substitution reactions. One you have come across the Reformsky reaction, which involves not an enolate, but it involves an organometallic in which carbon is bonded with zinc. So this carbon is electron rich, which is going to add to this carbonyl carbon. We are using ester. So this is the same reaction like Claisen-Schmidt reaction, but enolate is not used. Rather, enolate we are using organometallic. This is a major difference between Reformsky reaction and the Claisen-Schmidt condensation. Similarly, you have come across Darden's reaction. Darden's reaction over substrate is quite similar to the Reformsky, but we are not using organometallic. Here, this X is not only halogen, it may be any good living group in fact. So when we are reacting this with a base pick up a proton from here, generate an enolate, which adds to this. Up till here, this is very similar to Claisen-Smith condensation, resulting in the formation of this entity, but additionally it has this leaving group present at alpha position, which in Schmidt reaction it is not available. So this X group leaves. At the same time, this oxygen donate electronic density to this carbon, generating a three-membered ring, which can be ring open to form a antidiodes. All right. So this is you have already come across from olefin. If MCPBA oxidation we carry out, it always result in the formation of an epoxy group. Epoxy group upon reaction with the nucleophile, especially the water as a nucleophile in the presence of catalytic amount of amino acid, it always results in the formation of a antidiol. This is what you have already come across. So resulting two different enantiomers. These two, 3A and 3B, are enantiomers of each in fact. So because both of these are forming an equal ratio, so it shall be racemic, right? So this is the Darden's condensation. You can see that we are again exploiting this carbon where substitution is taking place, and this is going to be substituted with a electrophile, because this is an electrophile which is going to make a new bond. This is a new bond which is forming at this place. All right. So this is the aliphatic electrophilic substitution over substrate is electron rich. In most of the cases, this is carbonine, but in Reformsky reaction, this is in fact organometallic. Let's see, move further. Stobbe's condensation. Stobbe's condensation is a very unique feature in which in fact we are using a dicarbonyl system like this one. It is not necessarily it should be a mean 1,4 dicarbonyl or diester entity. It may be different to that. For example, if we are generating potassium tertiary butoxide is used because it slowly generate enolate. So this enolate, why we need slow enolate? Because if we are generating very fastly, then this enolate generated at this position or that position shall self-condensate with each other. This one of the molecules shall react with another molecule ester and making a new polymeric type alkyl chains. So a polymeric reaction is possible. That's why we need a slow generation of this enolate. As a result, potassium tertiary butoxide is used for this purpose, which basically pick up slowly this enolic proton from this oxygen, generate an enolate, negative charge there. In other resonance form, you shall see a negative charge at this position. This is presented. This keto form converts into enol form. Enol form in the presence of potassium tertiary butyl loses this proton, generate this enolate. Enolate further reacts with this ketone. Very similar way you have already come mechanical in Schmidt condensation. Similarly, you have seen in Reformitsky, etc. So this carbon transfers to this carbonyl carbon in a carbonyl type addition, resulting in the formation of this component number 5. Now what happens here interestingly, this oxygen is negatively charged. So because we have another carbonyl system present here, so this oxygen acts as a nucleophile. It adds to this, alright, and this oxygen takes this electron pair. It donates this electron pair and kicks out this ethoxy group from here, resulting in the formation of this compound number 6. What happens next? This takes electron pair off and hydrogen is lost at the same time, resulting in alpha beta unsaturated system. So at the same time, what is in fact happening in this case, this olefin is generated. This olefin is next to a ester, and we are generating a C double bond O negative. Because potassium with the ion available here, it form a potassium salt of that. Later on, when we work up, we add water to this reaction. So this potassium is replaced by hydrogen, resulting in the formation of potassium hydroxide. All right. So this is the compound number 2, which is formed in the end. First, it forms the salt, and then this salt converts into carboxylic acid. Now you see this part is coming from ketone, and this part is coming from this carbonyl systems. So how many carbonyls we are having? Just 3. You see, one, two, three, 4 carbons are there, but here we are having just 3 carbons. All right. So where is the one carbon has gone? You see here we are having one, two, three, 4 carbons intact. We have one, two, three, 4 carbons intact. All right. So, but in here we are having one, two, three. One of the carbon is basically present as a result. You see, it is making a double bond at this position. A double bond at this position. In fact, we have missed this CH2 carbon here. So we should replace a CH2 group here between carboxylic and this carbon. We have missed one carbon here. So again, so there are some mistakes that I shall replace, make a change, and I shall resend you so that to make the correction. In previous Darsans, there was also an error in arrow. So we have missed one carbon here, which is this CH2 carbon at this place. So CH2 shall be connected with this carboxylate, potassium salt, this one. So similarly, it shall also be CH2 this group. So we have missed this in this reaction. So anyhow, the application of Stobbe's condensation, let's see, we are having this not only esters, but dicarboxylic acid or dicarboxylates can be used. You see, that was 1,4 dicarbonyl, but this is not 1,4, this is 1, 2, 3, 4, 5. 1,5 dicarbonyl system. So 1,4 dicarbonyl results in the formation of a 5-membered ring, but you see this is making a 6-membered ring. This is the overall reaction. We are not using here esters, ketones. We are using acid halide. This X is chlorine, bromine, or iodine. So in this case, what happens first? Definitely, this carbon undergo deprotonation, generates a enolate here, and that enolate adds to the system. You see, we are just heating this reaction. Acid halide reacting with this 1,5-dicarbonyl system. The structure number 1 is commonly called homothalic acid, because if you remember, you have 2 carboxylic at ortho position, COOH here, COOH here. That is called thalic acid. but this is called homothalic acid. Homo, why? Because this CH2 is additional in this one. This is additional. That's why this is called homothalic acid. So as a result of this, it is not purely ester like in Stobbe's condensation. We are not reacting with ketone, but we are reacting with acid halide. So this results in the formation of this six-member heterocyclic ring system, which is commonly it is a natural product which is commonly called isocoumarins. All right, so this is a isocoumarine which is being synthesized by this procedure. Mechanism is presented here. Or we are not using any base in this reaction. Why? If you remember, this carbonyl system is conjugated with this through a enol form. Why? Because if it is present in such a form, this three double bond and a four double bond shell being conjugation have a higher resonance energy. Rather, it exists in this form, keto form. So here enol form is more stable. What happens? One of these OH loses hydrogen ion, H positive ion, and at the same time this carbon donate electronic density to this carbonyl carbon. Carbonyl oxygen take this oxygen negative charge, generate tetrahedral carbon. So in that case, this oxygen donate electronic density back, and this X leaves because X is a good leaving group. This is chloride, bromide, or iodide ion. So it leaves from here, resulting in the formation of, or you say, acylation at this place. So you see this is an electrophile which substituted this hydrogen at this tetrahedral carbon. This is a tetrahedral carbon where this electrophile has replaced the hydrogen. That's why we call this aliphatic electrophilic substitution reactions. Anyhow, we get this entity in this case. What happens next is quite interesting because we are having two carboxylic. Look at this carbon. This carbon is attached with two carbonyl systems. If you remember, whenever we are having two carbonyl systems present on same carbon, upon heating, it undergo decarboxylation. Why we are heating this? We are heating this just for this, to remove carbon dioxide. So at high temperature, it is although more than 150 degrees Celsius temperature. So at this temperature, one of this carbonyl leaf, this hydrogen donates electron pair back here, generating carbon oxygen double bond. And this carbon transfers at this place and it takes this hydrogen off. Results in what? This results in the formation of a enol form in fact. Enol means we are having a double bond here and we have a OH at that place, which shall tautomerize into keto form. It shall form enol first, then we shall tautomerize into keto form. So you see, this group is being replaced. This carboxylic which was present here is lost in the form of carbon dioxide, resulting in the formation of this compound number 5. If you remember, this fragment is coming from acid halide, this acid halide. Now, what happens next is very interesting. This oxygen donates electron pair density here, generating a carbon oxygen double bond. And this oxygen takes this electron pair off and donate this non-bonding electron pair to this carbonyl carbon, undergoing carbonyl addition. So we are getting a OH negative, OH at this place. What happens next? Because temperature is very high and high temperature always favor elimination. You shall see the next topic is elimination reactions. So we shall focus on elimination reaction today a little bit and then afterwards. So what happens in this case? The condensation stops condensation. This OH from this carbon and hydrogen from here. One leave with electron pair, other leave without electron pair, generating a double bond at this position. So this results in the formation of this entity which is commonly called isocoumarins. So this is a procedure how a natural product we can synthesize in fact. This is a little presentation what is a Stobbe's condensation. In fact, you see all of them are, we are exploiting the keto-enol tautomers. So this carbon, which is apparently commonly called active methylene, if you remember, I have already presented in lecture before substitution reactions that this carbon which is attached next to a carbonyl carbon or a nitro group or a imine, so this carbon is in conjugation with that and it results in the formation of a different tautomeric bond. Let's say we have double bond, this CH2 is attached with carbon double bond with nitrogen, commonly called imine. That imine take proton from here, results in the formation of a double bond here and a NH2 here. So it results in enamine. Imine, enamine nomenclature. So that is a tautomerism. Similarly, if we have a nitro here, so we shall get a Si nitro. So this proton in such cases, in nitro case, in carbonyl case, in imine case, in all cases, this proton present at this methylene carbon is in labile. This proton moves to on the nitrogen of imine or it transfers to the carbonyl oxygen or transfers to the oxygen of nitro group. All right. So these are the three tautomeric form which are very common, but oxime, nitroso-oxime are the other that we are not focusing on. So this proton at this carbon, CH2 carbon next to carbonyl, we are focusing all condensations, uh, aliphatic electrophilic substitution reaction. This is the you see tetrahedral carbon, sp3 hybridized. One of the hydrogen is replaced by a nucleophile. Here you see, sorry, electrophile. Here you see, this is the electrophile, unit is the electrophile. So we are making our substrate electron rich. In previous aliphatic nucleophilic substitution reaction, you have seen, we have this carbon electron deficient and a nucleophile is approaching this one. Here it is opposite. Our substrate is electron rich. That's why reacting with an electrophile. This is electrophilic aliphatic substitution reaction. In all such condensation, our substrate or tetrahedral carbon is negatively charged, electron rich. How we make this? By keto-enol tautomerism, nitro, nitro, Si nitro tautomerism, or we are exploiting another imine tautomerism. So we are exploiting them and resulting. But in this label, you have only carbonyl tautomerism we are exploiting. So I haven't exemplified the other ones in this case, in fact. So this is the another kind of the condensation. Let's see, proceed further. A couple of more. One is called Robinson's annulation. Annulation, whenever, in fact, in books you may find it called annihilation. A annihilation. Annihilation or annulation, both are the same, which mean ring formation. Annulation. Annulation or annihilation mean ring formation. Robinson's annulation, because Robinson was the scientist who first presented this. So this is in fact called Robinson's annulation. So what is Robinson's annulation? Robinson's annulation is the ring formation by Robinson. Now look at this substrate. First of all, what Robinson used? He used a 1,3-dicarbonyl system. You have seen in Schmidt condensation, we have synthesized these type of substrates. Synthesized substrates. Now, how this substrate is synthesized? Let's see if I break this bond from here. We have CH2, 3 CH2 carbonyl and all this C double bond O. This is ester group. Then one of this, if we generate enolate of this, so ketone have more in a power of enol generation, so it shall generate an enolate carrying a negative charge here. That shall add to this ester group and result in the formation of this result. So this is result of collision condensation. A collision condensation shall result in the formation of the substrate. When this substrate is taken, so it is, if you remember, this exists in this form more abundantly. Why? Because in this form, two double bonds are in conjugation. Rather, these two double bonds, look at this, 1,3-dicarbonyl system doesn't exist in this form. This is called keto form, this is enol form. Enol form is more stable. One three form is more stable than one. Why? Here two double bonds are in conjugation. So when two double bonds are in conjugation, it shall have a very minute resonance energy. That resonance energy, if you remember, cause stabilization. So it means these two double bonds are in more stable configuration. Rather, these two double bonds. So that's why this form is more available. What happens? It has a proton present here, OH. So it can lose this proton from here in the presence of a base. We normally use a base. So this base picks up this proton from here, generate enolate. This enolate undergo this addition. Now look at here, we are having a alpha beta unsaturated system. Now you have already come across alpha beta unsaturated systems we can generate by the reaction of ester with uh, if you remember collision Schmidt condensation. If an ester is reacted basically with some such systems, so we can generate alpha beta unsaturated esters. But here we are not using ester, we are using a ketone in fact. So this is a system that we can easily synthesize by collision Schmidt condensation. And this substrate we can simply synthesize by collision condensation. So these are the products of the condensation reactions. What Robinson has performed, he has used this entity coupled with this one because it shall generate a enolate at this position that I have highlighted. So this carbon shall make a bond, but it shall undergo conjugate addition. You have already come across direct addition and indirect addition. So direct addition and conjugate addition. So it shall follow conjugate addition because this is a carbon nucleophile. So we have just less than 1 minute remaining. So we shall log in again. We shall get this